Okay, thank you very much. It's a great pleasure to be here. I would like to thank organizers for the invitation. So I'm going to discuss some universal aspects of saturated memory capacity. So this lecture, from what I understand, is a little bit outside of the main focus. It's more interdisciplinary, and so the idea is to connect different ways of thinking about information processing and information storage, and to understand universal aspects, universal phenomena that are behind the enhanced capacity of memory storage and information storage, and to understand what are these objects, okay, what are the systems, what are their properties, and also whether we can, so irrespective of whether these are systems that are natural or artificial, and whether we can import some of this understanding for better information storage and processing in artificial systems like quantum computers or quantum neural networks, and so on. So I will start by, since it's a pretty interdisciplinary discussion, I will try to set the dictionary first. So the language. To set the language, I may repeat a few things that you know very well. Also, you can ask me questions anytime you want. You can simply speak up or interrupt me with whatever questions you want. We can make this interactive. Okay, so let me start with discussing obvious things. So the progress of our civilization is directly related with our ability to efficiently store information and process information. Now we can distinguish two ways of information storage, which we can call macro storage and micro storage. And the term is relative, of course. Now, in general, when we have a system as a physical system, for example, from the point of view of fundamental physics, we want to describe certain system. I don't know, it's a black hole or a neural network or whatever it is. It's a physical system, and it's a state of matter. Okay, so there is some fundamental theory, and this theory gives us all possible states in the whatever they can be actualized in the universe. So we normally store informations in the features. So these features can be macroscopic for a given observer. Of course, macroscopic is relative to an observer, or microscopic. So macroscopic, for example, here is Alice, our observer. Okay, and so we can agree with Alice to exchange a message, and the message can be an object, and we can say that if the object is I don't know, is a dog, then it's yes. If something else is a jar, then it's no. This would be a macroscopic way of information storage, not terribly efficient, obviously, because you don't have to make much effort to read this information, and it's also very energy consuming. Now, the micro storage of information is when we have to make a microscopic effort for resolving the state of the system, features of the system. For example, a book. If I give you a book, if you don't read it, you can think of it as the same macro state. But what distinguishes different books is the writing, is the text, and that's a micro state of the system. Okay. And now the elementary system that can store information, the simplest elementary system that can store information, we call it a bit, right? And the bit is anything that can be in two states. So it could be a switch on and off, it could be neuron on and off, and so on. So anything that could be in two different states, we can call them 0 and 1, excited, unexcited. Now, if we have capital N number of bits, independent systems. So then we can form a pattern, a memory pattern or an information pattern, which is defined by the state of these bits. So it's a sequence of zeros and ones. Now, so in this case, we can have number of patterns that we can form. It scales exponential with the number of bits, right? So bit is a degree of freedom. So it scales exponential with number of degrees of freedom. And we can define entropy of the system. For measuring information capacity, we can define an entropy. However, at this point, I didn't tell you what was the energy cost. For example, what was the energy cost of switching a bit from 0 to 1, all right? Or whether bits interact with each other. So in real systems, of course, they interact with each other, and there is certain energy cost, which is not uniform even. And correspondingly, the patterns that you can form, the memory patterns, they are not degenerate in energy. There is a certain energy split between them. And the split defines certain efficiency of the device to how it stores information, okay? Now, as I said, so this, in case when these patterns, so here I'm again plotting, we have n bits, and I'm denoting them by the two states by two colors, okay? Empty circle and dark circle. So each can be in two states, and so it forms exponentially large number of patterns. And if the states are hard to resolve, meaning that if you need to make a microscopic effort to resolve them, then we can talk about microstate entropy. Okay, so these are microstates of the system, meaning that an observer, a macroscopic observer, cannot resolve these different colors and different patterns. And microstate, in this case, entropy is the microstate entropy, and it scales a powered law with n, and this is important. Okay. Now, there is one important thing that we will need later. It will be actually very important. Now, if you have a system, if we generalize a bit to an elementary system that can be in d number of states, okay, instead of 2, in d number of states, let's say 7, okay. Let's say we have capital N bit number of bits. This is number of bits, and each of them can be in seven different colors. Okay. Their state we can call a color state. In this case, again, we'll have number of patterns. Number of pattern scales exponentially with n, but and correspondingly the entropy scales again a power law with n, but only logarithmically with the number of states in which each elementary degree of freedom can be. And so this is important, okay? So this will be important later. So what matters is the diversity of the degrees of freedom for the ability of the system to store information. What matters is the diversity of flavors of the number of degrees of freedom, and more than the number of states in which individually each of them can be. So now when we talk about capacity of memory storage, right? We have to make some definitions. Okay, so let's define capacity from the point of a physicist, because we normally care about energetics, okay, of the system. So we care about energy efficiency of the information storage. Okay. So energetic capacity of the memory storage we can define the following way. So here is this axis is energy, okay, and let's say here is the zero energy state, empty, let's say vacuum. And in order to store information, you have to produce a device, okay. So this device always costs some energy. You need some basic investment of energy to produce this device. So this energy is E, okay. We invest energy E. And then after this device has some little features which we can rearrange and form different patterns. there is certain number of patterns that we can form. So let's say these degrees of freedom are, I call them x's, okay? So x's. And so x1, x2, xn, these are degrees of freedom. For example, they can be bits, or they can be something that has larger number of states. It doesn't matter. So the x's, they can take certain values, different values. And so depending on the values of x's, we form different patterns, different memory patterns, different information patterns. Now, each pattern costs certain energy, okay? So let's say pattern x1, x2, xn costs energy E, and pattern x1 prime, x2 prime, xn prime costs energy E prime, okay? Then the important characteristics is the energy difference between these patterns, okay? Now, if the system can fit in a small gap, delta E, large number of patterns, okay, that will be one of the signs of energy efficiency of the information storage, okay, in the system. As I said, if you have any questions, you can interrupt me anytime. Now, this is one thing. So in other words, it's energy efficient when your system can store different patterns in a small gap, so that if you rearrange these patterns, they don't cost much energy. There is not much energy difference. There is not high energy barrier to go from one to the other. Okay. However, there is another characteristics because in general, not only we want to store information efficiently, but we also want to retrieve information efficiently. Okay. We want to retrieve it when we want and process it, or compare it with external stimulus and how it reacts to external stimulus, etc. Right? So therefore, there is also an efficiency of information retrieval, and this has different parameters. For example, how energetic, so how much energy you have to invest in order to retrieve information that you store in the system, and how time-consuming is the retrieval process, okay? And in general, in nature, there is no free lunch, so as we will see. Now, let me move to also introduce the concept. So many things that I will say equally applies to classical way of storing information, but also quantum information is important. So let me recall a few things. I want to make this lecture self-sufficient, obviously, so I don't assume any deep necessarily exposure to quantum mechanics or quantum field theory or whatever. Let me mention a basic concepts that we will need. Okay. So now quantum physics brings certain things with it. Okay. I will and in particular two things that will for us will be important is that there is an uncertainty relation. Okay. So this uncertainty relation tells us that there is no free lunch in how accurately you want to measure the energy of your system. Okay, energy. So the uncertainty in energy and uncertainty in time, they are related, and their product is non-zero. So this product is given by h bar, a constant of nature. Okay. Now, for my discussion here, it doesn't matter what precise value of this h bar is. H bar is very small in everyday units. That's why we don't in everyday life we don't notice quantum effects very efficiently. But more important thing is that this is something non-zero. Okay, for this discussion, that's what is important. Okay, in fact, I will say in most of my discussions, I will say h bar equals to 1. So we can use units in which h bar equals to 1 units. Okay, so therefore, this uncertainty relation is very important for information processing and information storage, because it tells us that the time scale, if you store information very energy efficiently, the time scale for resolving among different patterns is inversely proportional to the energy difference between these patterns. So if you decrease the energy difference, if you decrease the gap, you have to pay the price of investing more time, measurement time. So precision costs time. And this is very important. Another thing that quantum mechanics brings, important thing, is the superposition, the concept of superposition, okay? So what quantum mechanics tells us is that the systems, the fundamental feature, fundamental property of a system is to be in superposition of states, okay? Most of the systems are in some superpositions of states, okay? And no matter what basis you choose, okay? If you choose the basis and in that basis one system is in one particular state, most of the other objects and other systems will be in superposition. So the famous example for this is Schrödinger cat. You have heard it many times, a cat that can be in two states, okay? Of course, this looks strange from classical perspective, but there is nothing strange about it. This is what quantum physics tells us, that that's the fundamental feature of nature. What is actually the strange part is classical physics, because from here, for the systems for which we have many degrees of freedom, effective classical description emerges. That's why in everyday life, we don't see superpositions of cats. And quantum physics explains very nicely why we don't see superpositions of cats. Because it becomes exponentially hard if you want to make superposition of an object that consists of n degrees of freedom. Typically, it becomes exponentially hard, at least by exponent minus n factor, to prepare such a superposition. And then once you prepare it, it's extremely fragile, okay? So it makes absolutely perfect sense that we don't see superposition cats walking around in superpositions, or ourselves, we are not walking around in superpositions. However, for information processing and information storage, quantum physics gives us a fantastic opportunity, okay? Because, okay, immediately from information, from superposition principle, what follows is that now the concept of a bit has to be replaced by a concept of a quantum bit. Now, even if you define a system which is in two basic states, 0 and 1, okay? Two basic states. Generic state of the system, which I call psi here, this state, all right, is a superposition of the two with arbitrary, with certain coefficients alpha and beta, a complex numbers, and the complexity is extremely important here because phase is entered, which obey the relation, okay, the relation here. Okay. Now, another thing that superposition brings is that you can have qubits which are entangled, okay? And you heard this many times because this is a popular subject. Entanglement is a popular subject. For example, you can have a 2-qubit system, blue and red, and we can form a system can be in this state which is entangled. And that's great because we can exploit actually, explore and then exploit the properties of the entanglement for information processing. And in quantum computing, there is a very active research in coming up with different types of quantum algorithms for which uses entanglement, etc., for information storage and processing. So that's great, but what I want to focus on this lecture, and of course we cannot discuss everything in one lecture, although the subject is absolutely fascinating. So the question that I want to focus on is, where is the limit, okay? In other words, where is the limit of capacity of information storage, okay? And something very interesting comes out. So until recently, pretty recently, the only objects considered in this respect were black holes, okay? Now, in certain sense, once you take into account gravity and you have theory of gravity, you understand that, okay, black holes must be somehow saturating the capacity of information storage. Why? Because information costs energy, and if I put more information, I need to put more energy together, and eventually this energy will collapse into a black hole, okay? So it's not so surprising that black holes must be saturating the capacity of information storage. That's not surprising. Now, however, there were some surprising aspects emerging, okay? So black holes saturate the capacity of the certain bound. Okay, now there are several languages in which we can describe this capacity. For example, black holes saturate certain bound on entropy, bound by Bekenstein. And once they saturate this bound here, okay, and once they saturate this bound, their entropy takes a very interesting form. Their entropy is area in units of the Planck length. So this is Planck length. Planck length is the most fundamental length scale of nature. It's 10 to the minus 33 centimeters. For this discussion, this doesn't matter, the actual value of this Planck length. What is important is that there is a fundamental length scale which controls quantum gravity, and the black hole entropy, black hole information capacity, is scales as area in units of that length scale. Okay, and this was and still is considered as one of the mysteries of a black hole. Why area? Okay. Now, what we have understood, my collaborators and I, and this is a recent thing, and we are developing this. I'm trying to develop this picture as far as I can, is that surprisingly, an obvious question was never asked. At least I'm not aware of this question anywhere in the literature. And the question would be, you would say, okay, black holes are very special. They saturate information capacity, okay, and they are entropy scales like area, etc. But what happens to the other objects once we push them towards the point of saturating entropy capacity, information storage capacity? Because of course we understand that if I give you an apple and a black hole of the same size, black hole is very different from an apple. That's a triviality. But that's also a meaningless statement, because it's like comparing apples with oranges. In order to compare black hole with an apple, really, at the fundamental level, the right question that we have to ask, what happens with an apple if I push it towards saturating the capacity of information storage? And this elementary question, which now it looks elementary, was never asked this simply. Okay, for example, what happens with other quantum field theoretic states if we try to push them to saturate capacity of information storage? And what we discovered, and I wrote a few papers relatively recently on that, is that the fact is that all the known quantum field theoretic systems, and not just quantum field theoretic systems, and even non-relativistic type systems, they all behave exactly like black holes. Once you push them towards the saturating the capacity of information storage, they behave literally like black holes from the point of view of information storage and processing. And this is, on one hand, this is of course very important, because on one hand, this shows that there is a underlying universal phenomena which controls the capacity of information storage, irrespective of whether you're talking about black holes or gravitational systems or a neural network or quantum neural network or perhaps even biological. I don't know. I'm not a biologist, obviously. Or, for example, other systems like Bose-Einstein condensates, etc. Okay? First, this is very exciting for understanding, but also this is very important for importing these features for doing more efficient quantum computing and more efficient storage of information and processing in different systems. In other words, as I will discuss later towards the end of the lecture, we can manufacture a quantum computers or quantum neural network type systems, in laboratory, for example, with cold atoms, because we can push them, because now we know how to push them towards saturating the capacity of information storage. Okay, so, and this is very important and very exciting. So now, in order to set the reference point and to understand what is happening, and I want to explain to you what is happening. Actually, it turns out that the underlying phenomena is relatively simple. So we can explain it without very complicated mathematics, okay? So first let me give you some examples, okay? So let's compare black hole with some other reference point. So, and the well-known reference point is the human brain. Okay, here for simplicity, I took human brain to be something consisting of 10 to the 11 bits. Of course, human brain doesn't have qubits. These are normal bits or normal neurons, but it doesn't matter for comparing information capacity. This is fine, okay? Or if you want a quantum analog of a human brain, if you manufacture a quantum computer with the same number of qubits as human brain, you can compare this with a black hole. So if the human brain is approximately, I don't know what, probably 10 centimeters or something like that. And so a black hole with the same number of bits, qubits, would have the size approximately 10 to minus 27 centimeters. Of course, I'm not watching here factors of 2 and 3. These numbers are so large and or so small that these factors of 2 and 3, they do not matter. Also, of course, maybe biologists will complain that I took a 10 to the 11 only. Maybe I should have taken 10 to the 14 or something like that, but it doesn't matter. I mean, so just to illustrate the point. So you can see that actually the size of a black hole would be minuscule. Okay, so it's an extraordinary capacity of information storage, compactness. However, actually, with the second glance, we are not doing so bad because this black hole would be pretty heavy. So, of course, I mean, so not extraordinarily lighter than the human brain. I think it's around grams or 10 gram or something like that. However, the main thing is that this type of black hole with this size and with this memory capacity will not have a memory longevity. So it will not be able to maintain memory for only it will be able to maintain these memories with 10 to the minus 26 seconds. Okay, something like this, unless I made a mistake. But again, as I'm saying, okay, numbers are so large that it doesn't matter. So almost immediately it will lose on our time scale. Almost immediately, this black hole would lose all the memory. Okay. So we can take another reference point. So instead, we can say, okay, let's take a black hole which would maintain a memory on the time scale of a human brain. I don't know. I took 100 years. Again, I'm not a biologist, so but okay, 100 years looks like reasonable. A human brain can maintain memories over 100 years, at least certain important memories. And here, actually, the black hole which would maintain memory for that long, of course, is much heavier. It costs like 10 to the 6 tons, so it's much heavier than human brain. But also, actually, memory capacity is also pretty strong. It would have 10 to the 34 qubits. Okay, and the size would be also pretty small. Would be 10 to the minus 16 centimeters. So you see, there is sort of a competition between the two. Okay, I mean, I just took human brain as a reference point. I'm not claiming that human brain operates with the same uses the same operational rules that the black holes, although who knows. Okay. Now the thing is, so we set this reference point. Okay, clearly there is something extraordinary about black holes. Okay, in the compactness and ability to store information. And now let's try to understand how they managed to do that. Okay, now in science, when we want to understand a phenomena of nature, okay, suppose I give you a phenomenon of nature. I don't know, whatever, could be whatever. It could be a black hole, could be universe, could be a cat or something. And this one, or a bucket of water, for example, here. Okay. So this is water. Now, what is important? So, and then you see that this has some mysterious property. Okay. For example, you observe a bucket of water, and you don't know what the water is, but you see you walk out and you come back and you see that half of it is gone, so it evaporated. Okay, so you want to understand what this is about. So you have two ways to do it. Usually you have to explore both, and that's what we're trying to do. One is you create a microscopic theory of the phenomena. So you say, okay, let me create a theory of water. And in this theory, you say, okay, because it evaporated, probably it's not a uniform substance. Probably it's made out of small corpuscles. So it's the way of Democritus. And probably these corpuscles, they interact with each other and get energy from this interaction, and they collide with each other. And once in a while, because of collision, a corpuscle gets enough energy and goes out, okay? And then you try to take this theory and first compare with everything we know about water, empirical facts, and then make new predictions. For example, you say, okay, but now this theory predicts that if I heat water up, at some point it should start boiling. Okay, so this is one way to go. Another way to go is that you try to observe whether this mysterious property that you identify as mysterious is exhibited by other phenomena of nature. Okay, so for example, you see that water evaporates, you look for other liquids, and you see that they also evaporate. Then, even if you may not have a corpuscular theory yet, but you conclude that, okay, there must be some underlying phenomena that is much deeper than the particularities of the substance that I'm looking at, okay? And this underlying phenomena, you will arrive sooner or later that this is a corpuscular structure, certain type of corpuscular structure of a liquid, okay? So this is the approach that we are taking for black holes. And the approach number two, especially, I'm not aware of being taken. So we are talking about mystery of a black hole area law, more than 50 years or something. And this approach number two has not been taken. So we never asked a question, okay, let's look at other systems of nature with saturation of memory capacity. Do they behave like black holes? And the answer turns out they do. Now, let me set the stage for the next discussion to explain the underlying phenomena and how these phenomena can be used in different systems like quantum neural networks and so on. Okay, I mean, including quantum neural networks, of course, in many other places. But here I'm plotting. So the horizontal axis 1, 2, 3, n. These are number of degrees of freedom. Okay, let me call them modes or neurons. Sorry for my handwriting. I don't know. So neurons with the quotation mark, of course, because this is simply I'm using a degree of freedom that can be excited, unexcited. Degree of freedom that can have different levels of excitations. These levels of excitations I can label by colors. Okay, so let's say level 1, level 2, level 3, level D. Okay, you can use different terms. That doesn't matter. But it's important that you understand the language. So the language is, I'm saying, different degrees of freedom, I call them flavors. For example, qubits will be different number of qubit flavors. And the number of states in which these different degrees of freedom can be, I call them, here I'm calling them colors in quotation mark. Okay, so I'm denoting them by colors. So then this type of system with n degrees of freedom, okay, n neurons or synaptic connection, doesn't matter. Okay, whatever system has features in which you can describe by different states, being in different states. So what is the information pattern that is here? Obviously, information pattern is a line that connects these dots. Okay, so each connection gives you a particular information pattern. Okay, so because each connection tells you in which state each of these dots is. Okay, and their number is obviously in d to the power n. So it's exponential in n. And the microstate entropy scales as n times log of d. And this is important because this again tells you that it's not so important in how many internal states or how many different states each degree of freedom is. What is important is how the diversity of the degrees of freedom. Okay, so the entropy scales more with diversity than with the number of each individual degrees of freedom. Okay, so what matters are the flavors. Okay, as opposed to colors. However, there is a law of nature. And the law, so now we understand immediately. You say, okay, look, it's obvious. If I want to have a device that stores information efficiently, this device should be able to be to have many degrees of freedom that can be in many different states. So it should have high diversity of degrees of freedom, this device. Okay. Now there is a law of nature, and this law of nature says, and actually it's a deep law of nature. Now law maybe I should put in quotation marks because there are exceptions. We'll find exceptions from there. But this law says that usually if you want to create high diversity, that will also cost high energy. Okay, so it's very hard in nature to create diversity for free. For example, let's take angular momentum, right? So if I give you a system with very high angular momentum, okay, the angular momentum L, can have number of states in which the system can be projections on a z-axis, let's say, okay? If I have a particle of spin L, number of projections on a z-axis is 2L plus 1, okay? So there's large number of projections. This is diversity. So each projection is a degree of freedom, okay, right? So for example, electron will spin up, electron will spin down. These are two different degrees of freedom. Each can be 0 or 1, okay? So, however, this costs energy also. So typically, if you want to create a system with very high angular momentum, it requires high energy. And this is in general true. High diversity comes with the price of high energy. Typically, this is true. But again, there is a quotation mark in the law because there are exceptions. Now, a black hole somehow avoids this. Okay, and we'll try to understand how it avoids it. So let's again have a look at the efficiency of a black hole. So for example, let's take a black hole of the Earth mass. Okay, so if I give you a black hole of Earth mass, approximately it has a size of a centimeter. Okay, so if we take the entire Earth and compress it into approximately a centimeter sphere, it will become a black hole. Okay, so it will have energy of the Earth. This black hole has entropy that goes approximately, entropy of this black hole, of this one, is approximately 10 to the 66, okay? Entropy is 10 to the 66. Which means that this black hole has enormous number of memory patterns, exponent in power 10 to the 66, that they fit within a tiny energy gap. Now, this energy gap comes from the fact that black holes evaporate. Actually, most of the system, as we will see, most of the system of the enhanced capacity, they typically are also evaporate. They are unstable. And so this is the energy of the typical energy of the one Hawking quantum that the black hole of the Earth mass would emit. Okay, so since black hole of the Earth mass emits Hawking quanta of this energy, it doesn't make any sense to require the resolution with bigger accuracy, because after one light crossing time, it will lose this energy. Okay, so all the patterns, they fit within this. This is an enormous efficiency of information storage, extraordinary efficiency, because let's compare now to a naive way of storing information. So if I would now tell you, okay, I will tell, let's say Alice, our observer, okay, forget about black hole, all right? You are a particle physicist. You know that you have plenty of elementary particles available with all possible excitations. So create the diversity by putting together many particles with different angular momenta, etc., etc. For example, graviton. Even in pure gravity, you can do it. Okay, so graviton has excitations of different angular momenta, etc., etc., and use those excitations to store energy within a sphere of 1 centimeter size. Okay, so you put one graviton that spins like this, another one that spins like that. Collectively, they spin in this way. The whole diversity. You can, if you try to embed this amount of entropy, okay, the same memory capacity in this system. Of course, you cannot, because it will collapse into a black hole before you do it. But if you hypothetically imagine that you forget about black holes for a moment, and you say, okay, I will put this amount of information in this sphere, what will happen is that it will cost you energy which is 33 orders of magnitude heavier, exceeds the mass of a black hole. So by by doing same information storage, black hole gives us an enormous energy benefit. Also, these patterns that you would store in this way, they would not be degenerative. You would not be able to fit them in a tiny gap. They will be of the same split. So it would be nothing there would be no way to store energy efficiently in this way. Okay. Somehow black hole avoids it. And so how black hole does it? And here is the story reduced to bare essentials. Okay. So I would just want to explain bare essentials. This is the understanding we reached over several years. Okay. And it works. Okay, here is the way you can think about it. Okay. So here I gave you a toy Hamiltonian. Hamiltonian measures the energy of the system. Okay. And in this Hamiltonian, I've introduced degrees of freedom. You can think of them as neurons if you want. Okay. So these are degrees of freedom, which I call Y, Y1, Y2, Y3, Yn. Those are the ones that carry large diversity. Okay. In case of gravity, they correspond to gravitons or other particles with maximal angular momenta, okay? Because they have the maximal diversity. So there is an enormous number of those degrees of freedom. I call them memory modes, because if you want to store information efficiently, you have to use these degrees of freedom because they have the maximal diversity. However, there are also modes that essentially cost no energy. These are extremely soft. We call them soft. These are very low angular momentum and very low momentum excitations of gravitons, which barely fit in that size of a black hole, barely. So here I'm only taking one such mode because that's sufficient to illustrate the point. They are very little. Their number is very, very little. So they don't create high diversity. So I call them a master mode. So Z is a master mode and Y's are memory modes. Z is only one in this toy model. Z is only one and Y's are N. As you can see, if I ignore Z, if I would ignore Z temporarily, if I would ignore this term, this simply would be a Hamiltonian of N degrees of freedom, N oscillators or N neurons with huge energy gap epsilon. Now this epsilon typically would be of order of the Planck scale in gravity, enormous energy gap. So to excite each mode, it would cost energy epsilon. So in the absence of Z, this is what would happen. So in other words, if I'm considering only the situation where there is no black hole, situation without a black hole corresponds to this story. So this is no black hole. Okay, when Z is not excited, the master mode is not excited. If master mode is not excited, then any energy pattern that you want to store in Y modes costs an enormous energy cost. It's epsilon times of order N, because the reasonable energy pattern, is a sequence of zeros and ones. Typically, it has of order one ones and of the same order zeros. Okay, and so this is the energy cost. So this is the energy cost, enormous energy cost. Okay, so for example, for an Earth mass black hole, this would be energy cost, which would be 33 orders of magnitude higher than the mass of a Earth mass black hole. Okay. Now, what happens? However, gravity is smart and black hole is smart. So what black hole does is the following thing. Notice that black hole can compromise. So what it does is that instead of storing information directly into Y's, it also excites Z. Now, let's go back. So you see, if I excite Z, because interaction between Z and Y is negative energy because it's gravitational, gravity is attractive. So every time I excite Z, it becomes a little bit easier to excite Y. Z contributes negatively into the energy of Y, excitation energy of Y. Okay? So higher is Z excited, it is easier to excite Y. Excitation of Z itself costs very little energy. So that's what makes the mass of a black hole. So I'm not including in this Hamiltonian because that's irrelevant for this point. But there is a critical excitation. Critical excitation is 1 over alpha, 1 over the coupling constant. Okay? So in other words, there is coupling constant alpha, right? Sorry, here, right? Alpha sets the interaction strength between Z and Y. Alpha controls how energetically favorable is to excite Y when Z is around, or vice versa. If Y is excited, it's energetically favorable for Z to be excited. Okay, so this is what controlled, which is what controlled by alpha. In the neural network language, this sort of would contribute into synaptic connection, sort of. But okay, you have to establish a correct dictionary. Now, so what happens is that there is a critical value for Z, and once Z excited to 1 over alpha, the gap of Y's goes to 0, it just collapses to 0. So the energy, so the information storage in Y's becomes free. So the only energy cost is the excitation of Z's. No longer energy cost in excitation of Y's, almost no energy cost. There is a little energy cost because of quantum fluctuations of Z. Okay, the Y's are not exactly gapless, they still cost some energy. Okay, but that's nothing compared to what was before. So what is very important is what we are learning, and we are learning the following message: that if I have a system which has certain characteristic interaction between degrees of freedom that store information, and once the degrees of freedom, some of the degrees of freedom are excited to the saturation, we call it a saturation point or a critical point, are excited to the inverse of the interaction strength, a magic happens in the system. And some of the degrees of freedom, which before would cost enormous energy, now they collapse and become gapless. And now you can store information almost for free in those modes. This is what black hole does. Okay? Okay, so now there is a second point here. Okay, fine, but diversity of the modes that you can have, this is bounded by one of the most fundamental principles of nature, probably most fundamental principles in particle physics, but not only particle physics, which we call unitarity. Okay, so unitarity, evolution of the system must be unitary. Unitarity simply means that system preserves probability. The sum of all the probabilities should be 1. Okay, so this is unitarity. And unitarity, among other things, I don't have time to enter there, but physically it's understandable. Unitarity turns out that imposes a bound on diversity. Unitarity tells you that if you have degrees of freedom that interact with strength alpha, their diversity cannot exceed 1 over alpha. If their diversity exceeds 1 over alpha, your system would violate unitarity, and that's impossible. System cannot violate unitarity. So systems always make sure, consistent systems of nature, they always make sure that diversity never exceeds 1 over alpha. Okay, and this is very important. You can name, I don't know, infinite number of systems. I don't know, quantum field. You don't need to be in gravity. This is not exceptional gravity. That's the beauty of it. This is universal. In strong interactions. Actually, we wrote recently, Raju Balagopalan and I, recently we wrote a paper, my collaborator and I, we found analogous systems in quantum chromodynamics, there is this state, so-called color glass condensate. It's a known state, and it turns out that the color glass condensate is a state of maximal memory capacity, and it obeys precisely this type of unitarity bounds. So black holes are not alone, by no means. Now, then this combined with what I said, saturation, this combined with the fact that n, so this is unitarity, and the entropy goes as diversity, right? This gives a absolute bound of memory capacity that any system of nature must obey, okay? So there is a bound coming from unitarity that if you give me a system, the system could be quantum field theoretic system, could be a black hole, could be whatever, magnetic monopole, color glass condensate in quantum chromodynamics, quantum neural network, whatever. This is a bound that must be obeyed by the system. It cannot have entropy that exceeds the strength of the inverse coupling between the constituents, okay? This is an universal bound. And this is very exciting because now we can ask this question, okay? Are black holes alone in this? Okay. And I already answered this question. I just told you that even in QCD, color glass condensate has similar features. And excitingly, the answer is no. There is absolutely no reason for black holes to be unique in this business. And there are huge number of systems, consistent, theoretically consistent systems. And we also think that in practice, there are also many of those that saturate this bound, okay? Now, let me now, as a byproduct, okay? Now, of course, if you want to build systems that saturate memory capacity, this is the only bound you need to use, okay? However, I want to also tell you something which is incredible. Incredible thing is that black holes, I told you, black holes at entropy, which is area, okay, in Planck units. And then next thing I told you that there is a bound on information storage capacity. Now, for black holes, once I take gravitational coupling 1 over alpha, it exactly gives me the area. This is really incredible. We talked for 50 years about saying that black holes have area entropy. And we never said, but look, wait a minute. This is not just area. It's also inverse of the graviton coupling at that scale. That's a fact of nature. Okay, so the fact of nature is that graviton interaction strength at that scale scales as area. That's independent of whether you want to form a black hole or not. Just a simple fact of nature. Okay, so this is a property of gravity. And this explains why black hole entropy scales like area. Because black holes have to obey, they saturate, they have maximal capacity of information storage. And maximal capacity of information storage is the inverse coupling. And inverse gravitational coupling is area in the units of the Planck scale, period. Okay? Now let's move to the question of the time scale of the information retrieval. How fast? So now we suppose we have a system. I will give you examples of the systems, even in laboratory, the ones that we hope to produce in laboratory, the systems that saturate this memory capacity. But now the point is, suppose we have such a system which saturates maximal, which has maximal capacity of memory storage. Could be, again, could be neural network or whatever, or a quantum computer or whatever. So what's the time scale on which I can retrieve the information? Okay. And so again, it turns out that there is no free lunch. There is a bound. And the bound has this very elegant form. The time scale on which we can retrieve information from the system of typical, for the relativistic system of typical size R, for non-relativistic system, non-relativistic, this R has to be replaced by the typical frequency of the system, okay? Typical oscillation frequency of the system for non-relativistic. For example, for Bose-Einstein condensate. So, in other words, R, the size, stands as a typical de Broglie wavelength or size or typical oscillation, typical oscillation period of the system. So, you have the system that oscillates on this time scale. The question is, and it stores maximal information. So the question is, how long should I wait before I can retrieve the information which is stored in this system? And the time scale you have to wait is this. So you see, precisely what enhances the information capacity of the system to store information also puts the constraint and imposes a price on the time scale of the retrieval. So higher is the information stored in the system, the longer is the time scale of retrieval, okay? Now, this bound we can understand in very general terms. Actually, there is a very elegant physical way to understand this bound, where it comes from. Now, let's take a system of the size R. Suppose you have a system of size R, and that system has certain entropy, which measures the information capacity of this system. Okay, some kind of a quantum neural network, let's say. This system has this number of degenerate microstates. That's by definition, because if I told you that there is a, there is an entropy S, there is a certain number of degenerate microstates in the system. This number, and they fit within the typical oscillation time of the system. Now, because of this, obviously the minimal time that the memory modes must have, the minimal gap that memory modes must have, because the patterns have to fit within this gap. It's very easy to estimate that the minimal gap of each memory mode, each qubit, if they are qubits or whatever they are, okay? If each neuron, the gap has to go like 1 over S times R. Of course, since S has to be less than 1 over alpha, this translates into this. But this means that no matter what your system is, if it has entropy S, and this is absolutely general, it's in the bed of anything. So if you give me a system with entropy S, I know what are the minimal gaps that what are the maximal gaps actually. The gaps must be below this epsilon, whatever modes store information in this system. I don't need to know anything about the system. Okay, so the gaps are this. But then by quantum uncertainty principle, the time scale on which these modes can evolve must be inverse of the memory gap, inverse of the energy gap of these modes. Because you have a mode, right? So think in the following way. You have a qubit, and this qubit is in the state 0 or 1, okay? So there is a gap between 0 and 1, and that gap is given by this epsilon memory. Now, you want to perform a measurement. Okay, so you want to do some kind of scattering experiment or look at it at the qubit and read out the state of the qubit. So whether it's 0 or 1, this is the minimal time you have to wait simply by quantum uncertainty. And this fixes the information retrieval time from the system. So for generic system, the information retrieval time is the entropy times R. Okay. Now since my transparencies are handwriting, only in few places I put references. But okay, all these things are described in my papers, in my recent papers, actually. I have others also with collaborators, which I will later give references to. Okay, so now suppose Alice has this dilemma. So there is a system of maximal or enhanced memory capacity, and Alice wants to resolve the ability of the system. Okay, sorry, not the ability, but resolve the information stored in the system. Now, as we said, the information is stored in the state of whatever qubits they are. Or these qubits can also control the response of the system, okay? How they respond to external stimulus. Like in neural networks, the information is encoded in synaptic connections. So Alice, so this qubit contains certain flavors of neurons, certain flavors, and each of them can be in different color states. So in order to read out this information, Alice has to resolve flavor and color. So she needs to read out which flavor is in which color state, and this takes the time R times S. Now, there are two ways in which Alice can resolve this information. Okay, so one possibility is the following. Okay, here's the story, right? So you have a system with maximal memory capacity, right? The system saturates the bound on memory capacity. So the modes, the memory modes, I wrote them. I tried. I don't know if I succeeded. The memory modes Y, Y2, Y3, Yn, they are more feeble. They are less sharp here. So I just wanted to illustrate that they have very low gaps. Since they have very low gaps, they are blurry because they require more time, more observational time to resolve their state. Okay, so therefore Alice can wait. Alice can do two possibilities. Can choose among two possibilities. So Alice can say, okay, let me do the following thing. Let me not bother by examining in which state each mode Y is, okay, but simply wait until Z, the master mode, gets de-excited. This is what happens with a black hole, for example. Black hole evaporates. When black hole evaporates, the master mode of a black hole gets de-excited. And over time, the gaps of the memory modes, they grow. And so Alice can wait until the gaps grow and then do scattering experiment and resolve scattering or observation, or take a microscope, it doesn't matter, and resolve the state of Y's. Okay, so this is one possibility. Or Alice can decide not to wait and to do the following thing. Simply, there is a network. These modes are essentially gapless, and now Alice can simply scatter. In particle physics, we would say scattering. For example, if I have a black hole, I don't know in which state this black hole is, I would take an extremely soft light or extremely soft gravitational wave, and I would scatter it at it and try to then analyze the scattering process. Okay. What does it mean in the language of neural network? What does it mean? It means that there should be an external stimulus, okay, external layer of neurons, some axes. Let me call them axes, okay. And there must be a stimulus coming in form of x's that will resolve the state of y, whether it will somehow interact with y's. Okay. So y's have to respond to the stimulus, and then in this way we can analyze in which state these y's are. Okay. Now, both operations, they take the same time, because to wait until the master mode evaporates, to wait until the system loses the master mode, that takes long time, precisely given by the same number. Or in order to the scattering experiment in which we have to resolve extremely low frequency oscillations, extremely low gap excitations, the state of those, again, this takes very long time but just by uncertainty principle. Okay. So we get the same time scale for both operations. Now, so what is the lesson? So the lesson is that the saturated systems that saturate the bound on memory capacity. So in other words, saturated systems are the ones that saturate this bound, okay? This bound on memory capacity. They are forced to maintain information internally for a macroscopically long time. Now, this must ring a bell, because you probably heard many times that I don't know if you go to YouTube or whatever, people talk about black hole maintaining information for a very long time. Actually, sometimes people even say forever, but that's not simply there's no evidence for that. But we know that black hole maintains information internally for a sufficiently long time. Okay. Well, now we understand why. Because that's not a property of a black hole. That's a property of any system of maximal memory capacity. Any system of maximal memory capacity has exactly the same time scale of waiting before it can reveal the information stored in this system. And gravity has nothing to do with it. What this has to do with is a fundamental property of unitarity and fundamental property of physics. Okay. Of course, given rules of quantum mechanics, etc., quantum theory. Now, in most of the systems that you can produce, which have maximal capacity of memory storage, they are also unstable, like black holes. It's extremely hard to produce a system which would be macroscopically stable for the time scale longer than this. But that doesn't matter. Even if you manage to produce a device which itself is macroscopically stable on a time scale longer than this will still be the time scale of the information retrieval. There is no way to bypass this time scale. Okay. Now, again, let's try to understand this in very simple physical terms. Okay. Why a system that is saturated and has cheap way of storing memory pattern cannot give away the memory pattern? It's very simple, because here is the pictorial description of the system. Okay. So this is the part of the system that is saturated. Now, this system managed to make certain modes, certain degrees of freedom, certain vibrational, whatever you want. Degrees of freedom is a universal term. They can be neurons. They can be something responsible for synaptic connections. They can be harmonics, vibrating string, whatever. Degree of freedom is the universal language. We always store information in the states of degrees of freedom. So these degrees of freedom, if the system is saturating capacity of the memory storage, this means that the system managed to make certain degrees of freedom, set of degrees of freedom, gapless or almost gapless. Okay. Now, so imagine that there are these y degrees of freedom, y1, y2, y3, yn. Okay, these degrees of freedom. And for example, think in terms of a language. Okay, so imagine that this y is a language. So you wrote some message here, I don't know, in Russian, let's say. Okay, y1, y2, y3, yn. But because system is saturated, what the system did is that the Russian language became extremely cheap energetically. So it is favorable to write this language in Russian here. Now, here, let's say, now I want to extract this message. Extracting this message from the system means that I have to rewrite the same message that was written in this alphabet, okay, Cyrillic, let's say, right? Rewrite in a different alphabet. I don't know, let's say Latin, okay? But the Latin alphabet was not saturated. So the Latin symbols are floating around away from the system, but they are not saturated. So they cost much higher energy. The same content, the same message rewritten in Latin would cost much higher energy. That's why the system cannot give it away. It's impossible. There is simply an energetic barrier of rewriting the information from one language to the other. This is what is happening in a black hole, literally. In black hole, what is happening is that the certain degrees of freedom of gravitational excitations, and I will explain this in expert transparency, they become energetically cheap. The analogous, their counterparts, which are freely floating, they are extremely expensive. And that's why there is no way to rewrite this message directly. We have to wait very long, no matter what. Okay, so those of you that are familiar with elementary quantum mechanics or elementary quantum, I don't know, quantum neural networks or whatever, here's a toy Hamiltonian which you can exactly solve as an exercise and get convinced that this is what is happening. Okay, for example, here I have introduced system with toy model with 3 degrees of freedom. So there is a master mode. This is a master. Okay, there is the master mode interacts with memory mode X. Sorry, I had to call them Y. Sorry, the names are exchanged. So now the memory modes are X's. Okay, so this is memory. And Y's are freely floating modes. Okay. So every X has counterpart Y, which is freely floating, but Y is not saturated. Now, these are creation annihilation operators which create corresponding modes. Okay, so these are simply oscillators. So X, you can think of X as an excitation number of this quantum degree of freedom X, number operator, Y is number operator for Y, and Z is number operator for Z. I mean, for those of you that were exposed to elementary quantum mechanics, you know that these are standard commutation relations of the operators of creation annihilation algebra. For example, the creation operator acting on a vacuum creates one particle state, okay, and destruction operator acting on one particle state gives vacuum, and so on. Okay, for each mode, corresponding mode. So this system you can solve it exactly, and you can see immediately that in order that once I saturate the X and Z to move message from Y to X is impossible. Okay, so I'll give you later the exact solution for the similar system. I think I still have like 10 minutes or something, right? And so this is precisely what is happening in a black hole. For example, imagine, let's again take like a black hole of the 10-centimeter size black hole. Okay, I don't know. And now imagine that I store information, a picture of a cat or whatever object in this black hole. Now the similar picture of a cat, which is freely floating, with exactly the same, which would carry the same information about the cat, for example, for 10-centimeter black hole would cost enormous number as compared to the cat stored in a black hole. Okay, picture of a cat stored in a black hole. You can easily estimate this. And the reason is this Hamiltonian. So the key, the essence is described by this Hamiltonian. As simple as that. So simply saturated. The reason is that here degrees of freedom are saturated, and here they are not. So to carry away the picture of the cat, it must be carried away by degrees of freedom that are not saturated, and they cost a lot of energy outside of a black hole. And inside of a black hole, they cost nothing. As I said, this is the reason why black hole cannot emit information. But now we understand that there is nothing mysterious here. It's beautiful, but it's not mysterious, because that's the universal property for any system with saturating memory capacity. Now, finally, I will discuss one more feature. I still have like 5 minutes or something, right? Yeah, so I will discuss one more feature I want to mention. An interesting phenomena, again related with the saturation. I called it a memory burden effect, memory burden. And it's physically, it's very transparent. So what's happening is this. Once you have a system of that saturates memory capacity, suppose you have a system that saturates memory capacity, okay? Now, this means that the system is a device which can store a memory pattern at essentially zero energy cost, very little energy cost. Okay. So it's like an empty disk. It's like a hard disk. Now, the hard disk can be full or empty. Okay. So what saturation does, it prepares a condition, an optimal condition for information to be written here with almost no energy expense. But information may or may not be written. Now, imagine such a system, okay? Now, such a system, let's say, is saturating degrees of freedom y, okay? So Z is excited. So I wrote it as a fat blob, Z, excited, and it's saturating y's. Now, typically, if the number of y's is large, the pattern will not be empty. It's the probability for pattern to be empty is exponentially small. But it doesn't matter. Let me just simply focus on a pattern which is not empty. So if the memory pattern is not empty, this means that y's are also excited. Okay? They are gapless and excited. Typically, they are excited some zeros and ones, or maybe twos and ones. Well, that doesn't matter. So there is a sequence. Now, the thing is that imagine now that the system has a way of de-exciting Z, a master mode. For example, this is what happens for black holes. So black holes, they evaporate. They evaporate means that the master mode gets de-excited and gets transferred, the energy gets transferred into the outgoing radiation. So there is an external mode W that initially is empty. Z is occupied. Z is fat, W is empty, and then Z wants to go out. So which that Z wants to be de-excited and excite W. Okay, so there is a transfer of excitation from Z to W. Now, in order to achieve this, the pattern of Y's must also get de-excited. Why? Because if Y's will not get de-excited, then Y's will back react on Z, because it's not energetically favorable to go away from the saturation point. Because the same pattern that at saturation costs no energy, if you go away from the saturation point, will cost enormous energy. It's like, think about a device. You have created a device, and on that device you wrote some message. This message was very cheap energetically. Now this message prevents the device from being destroyed. Because if you destroy the device, the message cannot go anywhere. It has to be rewritten in outside modes, and that costs enormous energy. So this creates a back reaction effect, the so-called memory burden. Okay? And so, for example, this is a toy Hamiltonian, actually similar to the one that I described previously, in which you can see this explicitly. I mean, this is Hamiltonian in which we have mode Z, a master mode. This is master, this is memory modes, and Z oscillates into W, okay? I mean, goes into W. Now, time evolution of Z, this you can solve it exactly. This is given by this formula, okay? Where mu is the measure of how full is the memory pattern. So I call it a memory burden. So if memory pattern is full, you can see that this memory pattern prevents Z from going into W. So it stabilizes the system. And you can compare these two cases. For example, if pattern is empty, there's no problem. Z can very happily oscillate into W. This is an exact solution of this time evolution of Z, okay? So the master neuron will get de-excited, and the other one will get excited, the external one, W. But if pattern is full, that prevents Z from moving away from depleting, and so Z essentially stays constant. So the memory of the saturated system has a tendency of stabilizing the system. Now, this has very interesting implications for black holes. Okay, for example, in particular, as black holes, as primordial black holes, as dark matter candidates in the universe, because this opens up a possibility for black holes to be longer lived that we thought after half decade time. This is, of course, this is not conclusive yet. this is under consideration, under study. But it's also the same property is carried by other systems of nature. Okay, so here this pictorial illustration of this. Simply, this is this one saturated state and another saturated state, and it's easy to go from here to here if the memory pattern is empty. This is like butterfly without colors. And if the memory pattern is full, it creates a barrier, an energy barrier from moving away from the saturated point. Okay, so here I just illustrated this from the paper of my collaborators and I. For instance, these are numerical simulations in more complicated systems, and you can see in these systems, for instance, here that indeed the memory burden effect is at work. So for an empty pattern, the system depletes the master mode. For a full pattern, nothing happens. The master mode just stays here. Okay, so this is a paper with Lucas Eisenman, Marco Mitchell, and Sebastian Zell. We wrote a number of papers together. So let me finish with what are the prospects of generating this type of systems in laboratory. And actually, it turns out that there is an interesting direction in which we can look for this type of systems. Now, one thing I already mentioned, I said that even color glass condensate in QCD has these properties. And color glass condensate, okay, it is believed that this condensate has been obtained in high energy scattering experiments. However, so there is a prospect of achieving this type of saturated systems in laboratory setting with tabletop labs, for example, with cold atoms. Okay. Systems with already, so actually amazingly already, if we take, for example, a system in which we have n bosons with attractive interactions in a simplest box, okay, say on a ring or simply in a box, for example, on a ring, it has two phases, okay, where there is a uniform condensate or a bright solidon. This was well known. This is well known. But the most interesting part is between the phases. And between the phases, what happens is precisely the saturation. Okay, so when alpha n equals to 1, we get saturated system, and we get system of enhanced memory capacity. So this is the critical point where the system moves, this alpha n moves from small value to large value. Around the critical point, the large number of gapless degrees of freedom appear precisely in real time. And by the way, this system is exactly solvable. Actually, we numerically at least you can solve it. And we wrote a number of papers, my collaborators and I, Nico Winterkest, Alex Pretzel, Flassing, Cesar Gomez, myself, and others, Misha Panchenko, and so on. And so it's a very interesting system, the simplest one. So here, for example, you can see in real time, in real simulation, when you approach the critical saturation point. So this is what is written, what is displayed here. Here, what is displayed is the gap. Gap is displayed as oscillation frequency. So think of it as a neuron, which has a high frequency of high energy gap. Okay, so when we are away from criticality, away from saturation, this gap is very large, and so the oscillation frequency, as you can see, is very high. Away, over critical, under critical, and then there is this critical point where the oscillation frequency, you see this modulation. So this modulation tells you that there is a low frequency mode emerging around criticality. Okay, now this is a simple system of cold bosons in a box with simplest attractive interaction. So this makes us think that, okay, by the way, this is also a picture for the critical. This is a rainbow of these microstates. You can think of this as a wave function, rainbow of microstates that store information around that point. So you can store information in this rainbow. And the critical point, so therefore this makes us think that there are really new possibilities for doing this type of information storage and processing, and sort of simulating quantum neural networks with cold atoms and quantum computing with cold atoms, using the same rules of information processing and storage as black holes do. Okay, and this is pretty exciting. And I think I should finish here because I'm over time. Yeah, I'm not actually. I'm not over time.
Okay.
Yes, thank you very much for the attention.
Thanks a lot.